we're going to discuss about acid-base titration, although there's another titration that is included in the material, but today we're just going to do acid-base titration. So if we have an acid-base titration, so what we have here is a titration curve wherein you have the pH, okay, that is dependent on the volume of the acid or base that you're adding, the amount of the titrant. So it depends if you're adding an acid or a base. So if you're adding a base, you expect the pH to go up. Okay, if you're adding what we call an acid, you expect the pH to go down, some sort of that. Okay, so that is what we call the titration curve. A plot of the pH versus the amount of the titrant. Your titrant can either be an acid or a base. Okay, so the way that you're going to look at this one is there's an acid-base reaction that is happening. Okay, and when we have a curve, it is useful to determine the endpoint and dissociation constant of weak acids and weak bases. So there are several conditions that we have on the acids and bases that we have. So for instance, there's an interaction or an acid titration of a strong base versus a strong acid, or vice versa. Okay, there's a weak acid versus a strong base, or a weak base versus a strong acid, or both of them weak acid versus weak base. But the one that is common is the first three. And today we're going to go over some examples on these three, okay, at least two of them. Okay, now this is not new to you. This was covered already in Gen Chem 2, okay, in the acids and bases equilibria. So most likely this is just a more in-depth discussion about acid-base titration. So whenever we have a titration, so we have this what we call the titrant that is in your burette, and here you have the so-called analyte. Okay, so whatever happened here, okay, your titrant can be your acid or base. So if your titrant is the acid, the analyte is your base, and if your titrant is a base, your analyte is an acid. So that's how you do an acid-base titration. You cannot have an acid titrant and an acid analyte. Okay, so what you have is just one of them being an acid and the other one being the base. And it depends also if you have a weak acid or a strong acid with a weak base, or a strong base, or whatever combination that I have discussed to you earlier. So let's try to go with the classic strong base versus strong acid thing. So consider the titration of 50 ml of 0.02 molar of KOH with 0.1 molar of HBr. So if you're going to look at the picture here, what is the titrant? Anyone? What is here? So where is the KOH and where is the HBr? Anyone? So in this case that you have here, where you have a fixed volume, usually the fixed volume is your analyte. So the one that is the volume is changing, that is what we call your titrant. So we could say HBr is the titrant. So if we're going to look at how the plot would look like, what happened to the pH as you add more acid? Anyone?
It decreases.
It decrease, so it might look like this. Okay, so again, just like what we have before, the way that you're going to determine strong acid versus strong base or any acid-base titration is at equivalence point before equivalence point and after equivalence point. Here you can also have before titration. So what do you think is the pH before titration? Okay, so if you're going to look at the reaction, it is an H plus reacting with OH minus to produce water because both of them are strong base. Okay, so the K that you have there is the reverse of KW or the reciprocal of KW 10 to the 4, and that means it will really happen. Okay, now step 2 that you have here, just like what we did in the titration last 2 weeks ago, is to determine what's the volume of the other one, okay, at equivalence point. So this is just a simple what? C1, B1. So I could do C2, B2 here. And this is a C1, B1. So if you're going to look at this 50 times 0.020 divided by 0.1 to give you 10 ml. So what does it tells us? Less than 10 ml is before equivalence point. After 10 ml, this is after equivalence point. Okay? But before we start, what do you think is the pH? Before we start, that means at 0 ml HBr. What do you think it is? Anyone? What do you think is the pH before? So everything else depends on this one. So you have what? POH equals to negative log 0.020. That is equals to anyone? Plus
It's 1.69.
1.69.
Mm-hmm.
So that's the POH.
Mm-hmm.
So what will be the pH?
Mm-hmm. Yeah, 12.
So 14 minus 1.69, that is equals to negative log 12.30. Because this one is supposed to be what? 1698. So you can round it up to 1.70. So the start that you have there is 12.30. So we could say at zero volume, the initial pH there is 12.30. Okay. So after we add some amount, okay, as long as it's before the equivalence point. So what will be the pH when there's 3 ml of HBr that has been added? And the reaction is 3/10 complete because the volume equivalence is, the equivalence volume is 10 ml. So you can have this one, which is, I think, the shortcut. Okay. So the way that you have here, the fraction of your hydroxide that's remaining times the initial concentration times the dilution factor. And you get there the volume of the hydroxide. Okay. So you have from 12.3, it becomes 12.12. Or you can do the classic we could say calculation where you get the moles of the H plus and the moles of the hydroxide. So if you're going to look at this one, so you have what? 3 divided by 1,000 times, what's the initial concentration of your HBr? 0.1. And then the other one, you have what? 50 over 1,000 times 0.02, right? So what do you get there? Instead of doing this one, well, I leave it up to you which one you want to, what we could solve, as long as you know, okay, the correct answer. So 3 divided by 1,000 times 0.1. So you have here around 3 times 10 to the negative 4. And the other one, 50 divided by 1,000 times 0.02. So you have 1 times 10 to the negative 3. So if you're going to look at this, so you have what? 0.001 minus 0.0003, giving you 0.007 moles of hydroxide divided by the total volume, which is equals to 53 divided by 1,000 ml per liter. So what do you get there? You get the same amount as this one, right? Please check. So I told you, whatever way you're going to do, as long as you get the correct answer, it's fine with me. Now, remember, this is hydroxide because that's the one that is present in excess. So once you get that, you can get what? So that's the concentration. You can get the log of that. That is equals to what? If you're going to get the negative log of 0.0132, I get around 1.88. So that's the POH. And when I get the pH, it's 14 minus 1.88, which is equals to 12.12. So it's the same as the other one. So I just gave you 2 ways on how to solve the pH before the equivalence point. So analyze. And if you have question, let me know. Question? Any question, class? Now, if not, we go to the next.
Dr. Mojica, can I just double check with you quickly? You said that there's no lab this week, right?
Yeah.
Okay.
Now, at step 4, at equivalence point, what's the pH? Anyone? So remember the titration last week? you just get the pH equals to whatever the KSP. So here, the pH is just equals to 7 because you have a strong acid and a strong base. So what happened during that time? So your point 001, okay? And then you subtract it also with 0.001. So what will happen? You end up with none of the acid or none of the base in excess. So they have the same amount. So the equivalence point is what we call equals to 7. So this is where you have equal moles of the OH minus and the H plus. That's only true if you have a strong acid and a strong base. Okay. Now, whenever you pass by the equivalence point, so the one in excess now is H plus. So let's say 10.50 ml. Okay. So at this time, you have the H plus as the one in excess. So in this case, you can have the initial concentration times the 0.5. Where do we get the 0.5? So that's 10.5 minus 10, which is the equivalence point, divided by the total volume. So it will give you this amount, okay, and then get the negative log of that, and you will have 3.08. Or you can do it like what we're doing, but this time, which one is the one in excess? It's already the H plus. So you can do it like this. So in the end, you will have what? 0.00050. 1, 2, 3, 4, 5. So 5 times 10 to the negative 5 divided by 60.5 divided by 1,000. So you just converted the volume there into liters. So if you're going to get the volume there, okay, that's the corresponding amount that you have is the same value as this one, right? So that's moles over liters here. So 1,000 ml per liter. Try to do it. Question? So that's how you do titration of a strong base added with strong acid. So it starts at, if we're going to look at the plot, I think I have the plot later here. So this is how it looks like. So I started at around 12.30, if I'm not mistaken. So at the beginning we have right, just to make sure so 12.30 and then 12.12 So 12.30 here. And then when 3 ml was added, that's around here, that's 12.12. And then you have 7. And then when you add around 10.5, okay, it's around 3. We're going to look at 3.08. So this is how it looks like. So when you have around 10.5 ml. Okay. Now let's go to the more challenging one. So what happens if you have a weak acid and a strong base? Just like the case of this 50 ml of 0.02 molar of MES, that's an acid. Okay. That has a pKa of 6.27 with 0.1 molar of NaOH. Okay, so if you're going to look at the reaction, it will be driven forward because of the presence of the hydroxide, even though this one is a weak acid. Okay, the strong base is enough, strong enough to make the reaction to occur. Okay, so with this condition, okay, we can look at this so-called reaction. So you have an HA here. So see the difference in a strong acid versus a strong base is an H plus OH minus. But in a weak acid, we have an HA reacting with an OH minus to give us A minus and water. Okay. And then the next thing that we're going to do, just like before, is to determine the equivalence volume, because that's where the moles of your acid is equals to the moles of the base. So this is just the classic C1B1 equals to C2B2. And this is the same condition as the strong acid, strong base. You have a 50 ml of 0.020 NaOH earlier with 0.1 HBr. So the same thing here. The amount of your base here is just equal to 10 ml. So you can do a condition wherein you do it before you add the base. So in doing that, that is just equals to what? What if I ask you to determine the pH at 0 ml, 0.1 molar NaOH? How are we going to solve that? So you need this, and you need this one. That is a classic what? HA, okay, dissociating to give you H plus and A minus. So what do you have here? 0.020. You have 0, 0, and then you have minus X, and then you have plus X, and then you have plus X here. So this is equals to 0.020 minus X, and then you have X, and then you have X. Now you have to get now the pKa, so that's just 10 raised to negative 6.27. That's the negative, that's the Ka value. So once you get that value, that is equals to X times X over 0.020 minus X. And again, we can just say that it's the same as this one. So if we're going to get 10 raised to the negative 6.27, that is equals to this. And you have the X squared there over 0.020. So you cross multiply. And you have an X squared, and then you get the square root, whatever the product that you have here. So point times 0.020. Get the square root of that. So I get around 1.036 or 1.04 times 10 to the negative 4 X. And that is the H plus. So my starting pH would be the negative log of that. Which is 3.98. So try. So this is the pH before you add the NaOH. So the next thing that we're going to do is restart. So remember, what do we have initially? 3.98. And then we added some amount. So this is the same as the one that I have what we called salt before any base is added. So around 3.99. So I get 3.98 because I have 1.04 times 10 to the negative 4, the one that I use. And then before any equivalence point, before the equivalence point, whenever you add, okay, before 10 ml, the calculation could be based on what we call the Henderson-Hasselbalch equation, which is the buffer. Okay, so let's say you add 30% or 3 ml of your volume's equivalent point, you just use the Henderson-Hasselbalch. So you have there the pKa and then the negative log. So if you add 3 ml, okay, so of that 3 ml, what will happen? You're going to produce, remember, you have it like this. So initially you could say 10 ml is the one that you need, okay, to do equivalence point. So you have 10 here and then you add what? 3. So what will happen? You subtract this by 3, you subtract this by 3, you form 3 here. And now this becomes 7, this becomes 0, and this becomes 3. Okay, so 3 over 10, and this one is 7 over 10. So that's where we get this value here. So when you add the 3 ml, it's now 5.90 pH. Now, there's a special case here, okay, wherein you add, what if you add 50% of your equivalence point? So what happened to that? 50%. So 50% is 5. You add 5 here, you utilize 5. So what do you form here? You form 5, still 0. But this one, you have 5. So you have 5 here. So your numbers here will now be equal. 5 over 10 over 5 over 10, or 1/2 over 1/2. So you just cancel out. Okay. So negative log of 1 is equals to 0. So your pH is just equals to pKa, which is equals to your 6.27. So we already get the 3 points in the weak acid versus a strong base calculation. Okay, now at equivalence point, so that's where they're equal. So what will happen if we follow it like this? What will happen here? So if we have here the HA plus OH minus producing A minus. So this is 10. So if you say equivalence point, this is also 10. So what happened here? Minus 10, minus 10, but this now becomes plus 10. So you don't have here, you don't have here, but you have your conjugate base that form. And that conjugate base can hydrolyze in water because the conjugate base that you have is that of weak acid. So whatever you have that will hydrolyze okay, giving you, okay, the source of your pH, which in this case is hydroxide. So it gives you an idea if you have a weak acid and a strong base, the equivalence point is in the basic pH. Okay, so if we're going to look at the number, so this is the initial concentration of your weak acid. This is the initial volume of your acid over the total volume, which is just what, 50 plus 10. And you have here as the total volume of the solution. And here, that is the moles of your A minus. Okay, so 0.0167, that's the concentration of your A minus. So once you allow it to react here, so you will have this relationship. Okay, so that's A minus. Okay, so if you're going to look at the relationship here, so this is what, KB equals to HA times OH minus over A minus. And what's the KB that we have here? So we need to get it from the given Ka. So 1 times 10 to the negative 14 divided by 10 raised to the negative, what's the Ka given, pKa? 6.27. And you have your X times X over 0.0167. So we already dropped the minus X there. So try to see if when you solve this one, this is the number that comes out, which is a hydroxide. One exponent negative 14 divided by 10 to the negative 6.27. So I get the 1.86 times 10 to the negative 8. Okay. And I multiply it with 0.0167 and then get the square root of that. And that gives me this number. So this is your hydroxide. And if you're going to get the negative log of that, that is equals to 4.75. Subtract it with 14. So you get the 9.25. Analyze. Question? So that is at equivalence point, and it makes sense that 9.25 is at basic pH. So a weak acid versus a strong base, the equivalence point is at basic pH. Now, what happened after equivalence point? So in this case, the one that is in excess now is the base. Okay, so let's say if you have 10.1. So how are we going to do this thing, 10.1? So you have the initial concentration of the hydroxide, which is 0.1 times 0.1 divided by, I think this should be at 10.1. That's the difference there. That's the mistake. Because this is after you add 10.1 ml of your hydroxide. So if you have that, so 0.1 times 0.1 divided by 60.1 So I have here 1.66 times 10 to the negative 4. So just to remind you, this is a 10.1. Okay. So this is the hydroxide. So you get the POH of that negative log. So that's around 3.78 plus 14, or subtract it from 14. So you have 10.22. Question. And if you're going to look at what we have just discussed, this is how it looked like. The starting point here, which is 3.99. And then when you have a buffer on this one, so this is at equivalence, no, not equivalence point. This is where half of your equivalence point, where the pH is just equals to your pKa, and this is the equivalence point that you have, and this is what you have. So as you could see here, the pH at the equivalence point is higher than 7. Now, you can look at this, what we have discussed is this one. So at the initial pH or initial point, we solve it like a weak acid problem. And then between that, okay, until the equivalence point, you solve it like a buffer. Okay. And then at equivalence point, you solve it like a hydrolysis of the salt. And the excess is just equals to what? The negative log of Kw over the hydroxide concentration to get the pH. So that's the summary of what we have done. Now, if you do it the other way around, which we have not discussed, titration of a weak base with strong acid is the same. So the initial point that you have there, you solve it like a weak base problem. And then before the equivalence point, they act as a buffer. Okay. And then at equivalence point, it is the hydrolysis of the salt, or the pH of the salt, how you get that. And then the excess H plus that you have there, you just have to get the concentration of H plus and then get the negative log of that to get the pH. So this is the summary on how we solve titration problem. So if we're going to look at some other example like this one, titration of 40 ml of 0.1 molar HCl with 0.1 molar NaOH. So we know the equivalence point, since they have the same concentration, to be 40 ml, as seen here. And the one before that, this is what the pH would look like. And at this pH, you can either use two indicator, either the phenolphthalein, where there will be a change between pH 8 to 10, or a methyl red, where there's a change between pH 4 to pH 6. Now, the thing that you remember in the strong acid, strong base titration curve features, the pH will start out low, reflecting the high H plus of the strong acid, and increases gradually as acid is neutralized by the added base. And then out of a sudden, the pH rise steeply. So this occurs in the immediate vicinity of the equivalence points. If you're going to look at this, it just rise steeply. Okay, so that's happened when it is near the equivalence point. So this type of titration would have pH 7 as the equivalence point. So beyond this steep portion, the pH increases slowly as more base is added. So if you add more base here, okay, the pH will just increase what we call slowly. And if you're going to look some sample calculation of a strong acid, strong base, so this is another way, the one that I have did, what I did in addition to what was discussed. discussing the initial moles of the H plus minus the moles of the OH that was added. Okay. So at the equivalence point, you just determine which one is present in excess. So at the equivalence point, they have the same. So that means they have a pH 7. And after the equivalence point, you just look at the one that is in excess and divide it with the total volume. Okay. Now, look at the difference between a weak acid strong base titration and a strong acid strong base. So the strong acid strong base is here. Its pH started slowly, but if you have a weak acid, this is where it starts. Okay. So again, it's a weak acid problem here, then the buffer region. Okay. And then you have here the salt problem, and here you have the excess hydroxide problem. So if you're going to look at the difference between the two, the initial pH is higher for weak acid versus strong base. And a gradually rising portion of the curve called the buffer region appears before the steep rise in the equivalence point. So the pH at the equivalence point is greater than 7. And the steep rise interval is less pronounced. So as you could see here, it's not as pronounced as the one that you have here in strong acid, strong base. Now, if you have a weak base, strong acid titration curve, which we never did, so this is how it looks like. So you started at the high pH and then you add an acid, so the pH will go down. And just like the weak acid, strong base thing, it's just like a mirror image of this thing. So initial pH is above 7, and then you have the decreasing portion of the curve, which is the buffer region. Okay, and then the pH of the equivalent point is less than 7. Okay, and the pH decreases slowly as excess strong acid is added. As you add more acid here, it doesn't drop too much as the one that you have initially. Now, in case you have this so-called polyprotic acid titration, so what you have there is just two regions that represents the available hydrogen that you have. So for instance, if you have a sulfurous acid here, okay, so this is the first buffer region, which pertains to what? The Ka1. And this is the second buffer region, which represents Ka2 or pKa2. This one is pKa1. And if we're going to look at the features of the polyprotic acid titrated with strong base, the loss of each mole of H plus shows up a separate equivalence point, but only if the two pKa's are separated by more than 3 pK units. And the pH at the midpoint of the buffer is equal to the pKa of that acid species. And the same volume of added base is required to remove each mole of H plus. Now, if we're going to look at this, we're going to compare, let's say, on the first plot here, the strength of the acid. So what can you see here? The stronger the acid, the more pronounced is the equivalence point. So look at the strong acid, it's the whole thing here. If it's a Ka1 that's 10 to the -2, it's around that. If it's 10 to the -4, it's just that one. So it becomes narrower and narrower. The same thing with the effect of the concentration here. Okay, the higher the concentration of your weak acid, the more pronounced is the equivalence point. So look at the 20 millimolar, so the black one there, and then the 2 millimolar, it's just this the region that you have there, and then the 0.2, which is the broken line. So they become less pronounced as the concentration of the weak acid decreases. Now let's go on the indicator. Why do they change color? Okay, what's the chemistry of the indicator that we have? So if we have thymol blue, and we're going to look at the pKa of thymol blue. So at pKa, at pH lower than 1.7, it is red. It is red because everything is what? Protonated. Okay. And then what happened? When you increase the pH, it becomes yellow because one of them, what do you call this? What is transformation that you see here from your organic? Anyone? Is that your things like this? Ketoenol? Transformation? So one of the hydrogen lose. Okay, and what happens? You form a ketone from your phenolic group here. And from red, it becomes yellow. Now, if you increase the pH furthermore, the hydrogen that you have here is deprotonated. And in that case, at pH higher than 8.9, you have the blue. That's the transition that you have there. Okay, from red going to yellow and then going to blue. So what do you think is the transition point here? What color? Anyone? And what do you think the color that you have here? From red to yellow, what's the transition that you have? Anyone? Hello? So what do you think is the color here? From red transitioning to yellow, what's the transition color before they become yellow? So red plus yellow will give you the orange color. And then the one here, yellow and blue, will give you green. So that's the changes that you have. So thymol blue, you can use it at different pH range. Now, the classic phenolphthalein that we always use. So if it's less than pH 8, it's a colorless phenolphthalein. So you have everything there as protonated. And then at higher pH, higher than 9.6, your colorless will become pink. And this is due to the deprotonation on this side and the ketoenol transformation on this side also. And there's a breaking here. Okay. Yeah, it becomes a carboxylate group if you remember your orgo. Okay, now you can also have a phenolphthalein at low pH, which is different. From colorless, it can become orange-red because all of them are what we call protonated. Okay, and at much higher pH, around 11, okay, you can have a colorless phenolphthalein. So it's just the same thing as the one that you have there. So if you're going to look at how to choose the right indicator in an acid-base titration, so you always have to look at the transition, the pKa, where they change color. So for instance here, so you have a titration wherein there's a equivalence point of 5.54. So you have to use an indicator where they will transition, okay, above and below 5.54. So you can use a bromcresol green. So from blue, it becomes yellow, or a bromcresol purple, okay, wherein it's purple higher than 5.54 and it's yellow at pH lower than 5.54. Okay, so here are, we could say, the transition point that you have. So if your transition range is between what? Acidic pH, okay, you can use the one, any of one here. Okay, if it's at basic pH, you're going to use the one that you have here. So phenolphthalein is between 8.0 and 9.6. So this is, I think, the best way to do the presentation on which indicator that you need to use at a certain pH. So if you're given a question like here, like a multiple choice question, so the one that is given to you here is what we call the transition range. Without the transition rate, you cannot what we call answer it. So it will be given to you here. And then you will ask which indicator can be used at this pH range. Okay, or which indicator can be used at pH range 5. So your choice would be either this or this. You cannot use this one because at 5, it is what? Blue, below and above 5. And this one, it's yellow, below and above 5. Okay, so there's no way for you to determine the difference if the pH range is around 5. So for instance, if you have it around here, 9, your choice can be this or this. So why did I say I included this? Because there's a range that it will change between here. Okay, and also between this one. Now, if you have what we call 11, you can still use this one because there's a different color below 11 that is different from above 11, or the perfect choice that you have is this one. So that's what we have for now. Question? Question? Before I turn off the recorder.
Are you gonna post this?
Yeah.